All right, so we're shared our screen, and this is our presentation. Good afternoon, good morning, or good evening. My name is Drina Miyapara.
Hello, good morning, good afternoon. My name is Aisha Sisi.
And today we're going to be talking about our prime refrigeration cycle. So this is our refrigeration cycle schematic diagram. We're starting off with our evaporator, where the heat is being added, absorbed into the evaporator, where the working fluid is also entering. So to talk further, I'm just going to mention we chose our working fluid as ammonia, and we'll talk further on why we decided to choose that. But once we are entering the evaporator at stage 1, as you can see on the bottom right, we're entering a compressor, where that working fluid is going to be at a high pressure and it's being compressed, and our work is going into the compressor. So at stage 2, once the working fluid passes the compressor, we're entering a condenser where heat is being rejected QH, as you can see on the top in the middle. So the condenser functions, the liquid passes through out of 3, and at stage 3, we're entering a turbine adiabatically. So either a turbine or an expansion valve. The purpose is to lower the pressure and temperature so that the working fluid can come out as a liquid, vapor liquid. And it's gonna start over at the cycle, starting at the evaporator. So at stage 1, we're starting off at a saturated vapor with a delta H of QC. And then once it exits the evaporator, we're heading at the compressor, which is saturated vapor, and it comes out as a superheated vapor. So at stage 2, we have a delta H of work. So once it's coming out, we're heading to the condenser. At the condenser, what's coming out is a saturated liquid. And at the saturated liquid, we have a delta H of QH. So once it's coming out, we're entering the turbine or expansion valve, where we have the purpose is to lower the temperature and pressure for the working fluid. So once it's coming out, we have a vapor liquid. So those are the states at each stage. So the delta H equals 0 at the turbine or the expansion valve. So this is our cycle, but we were given, as you can see on the right side, a T1 low minimum and a T1 low max of -5 degrees Celsius to -15 degrees Celsius. And then we were given a T2 high max and T2 high min of 25 degrees Celsius and 30 degrees Celsius of our functioning parameters.
So here are the equations where we can use according to the first and the second law of thermodynamics, where the change in entropy is equal to the integral in Q over T. Also, the work is equal to the mass flow rate over the delta H. The mass flow rate is QC over delta H, and then the Q actually is equal to the delta H times the mass flow rate, and we have also the ideal gas equation.
So looking here is our ammonium pH diagram. So we use our pH diagram to determine our values, our enthalpy, entropy, our pressures and temperatures, and then also quality. So on the bottom right, looking there, that's our stage 1, which is our evaporator. And then on the top, as you follow those 2 lines, those are our compressor. So we're having isentropic and our actual. So the one on the left is our isentropic, the one on the right is our actual, and then following along at a constant temperature, which is 45 degrees Celsius. So that 45 degrees Celsius, we're heading to 3, that is our condenser, and then dropping down following a constant entropy, we hit stage 4, which is our evaporator. So, our expansion valve. So from there, we have a constant temperature of -30 degrees Celsius. So we determined our states and our pressures following along those constant lines. So given the pH diagram, we determined our refrigeration cycle parameters. So let's start off with our temperatures at each stage. So we're given -30 degrees Celsius, 45 degrees Celsius, And our actual we had to determine due to our actual work, and we determined to be 230 degrees Celsius. Stage 3, we have 45 degrees Celsius. Stage 4, we have negative 30 degrees Celsius. So pressures at each stage. State 1, we have 0.12 megapascal. State 2, isentropically. And actual, we'll have the constant temperature, as long with state 3 as well, 1.89 megapascal. And then at state 4, which is our expansion valve, we have 0.12 megapascal. Following along with entropy, in kilojoules per kilogram times Kelvin. At state 1, we have 6.10. At state 2, isentropically, we have 6.10. At state 2, actual, we have 6.50. And then at state 3, we have 6.10. And lastly, at state 4, which is our expansion valve, we have 1.80 kilojoules kilogram times Kelvin. So now enthalpy. At state 1, we have 1,410 kilojoules per kilogram. State 2, isentropically, we have 1,850. State 2, actual, we have 2,000.7. At state 3 and 4, we're going to have the same constant enthalpy. So we have 420 kilojoules per kilogram, along with the quality. So at state 1, we have 1 because it's on the saturated liquid line. And then at state 2, isentropically and actual, it's superheated, so we can actually determine the accurate number, but of course it has to be greater than 1. And our state 3, we have 0. And our state 4, we have 0.27, which was also 27%. So along here, with our given entropy, enthalpy, we created a TS diagram. So as you can know, you have constant entropy and you have constant temperatures at the 2 levels. So we draw TS diagram. As you can tell, that's how it look at stage 1, stage 2, stage 3, and 4.
Okay, so here's come our calculation part. And we first calculated the isentropic work, which is the H out minus H in, which is H2 minus H1. And then we get 440 kilojoule per kilogram. And then after that, we calculated the actual work, which is the isotropic work divided by its efficiency, which is 440 kilojoule per kilogram divided by the efficiency. And the efficiency, we researched it online, and we found, we chose the value of 0.75, and we got 586.7 kilojoule per kilogram. From there, we calculated the H out actual, where we add the isentropic work plus the H in, and we got 2,000.7 kilojoule per kilogram. And then after that, we calculated the latent heat in the evaporator, which is also the heat in, where we by the delta H, which is H1 minus H4, which is 4,410 minus 420 kilojoule per kilogram, and we got 990 kilojoules per kilograms. And then from there, we try to calculate the mass flow rate by first multiply the thermal load by the
Safety factor.
the safety factor, which is 1.3, and then we got 2,574. And then from there, we converted the kilowatt into kilojoule per minute, and then from there we converted to per second, and then we know that the mass flow rate is equal to the Q flow rate over the QC. So from there we calculated, and we got 0.04 kilograms per second. So, and then we also calculate the heat in the evaporator, which we converted the heat by multiplying by the mass flow rate, and we got 39.6 kilojoules per second. We did the same thing too for the compressor, like the work in the compressor isentropically. we multiplied by its mass flow rate, and again we got 17.6 kilojoules per second. And we did also, we converted the actual work into actual work flow rate, and we got 23.626 kilojoules per second. We did the same thing for the condenser out, and the condenser isentropically, and actual. For the actual, we got negative 63.23 kilojoules per second. And for the isentropic, we got negative 52.2 kilojoules per second. We got a negative value because it's in the condenser and the heat is rejected. So that's why the value is negative. And also for the extension valve, we got the same entropy because it's isenthalpic. So, and from there, the program asks us to calculate the coefficients of performance, which is the Q in divided by the work, the actual work. So we divided the Q in that we calculated by which is 39.6 divided by 23.628, and we got 1.68.
So here we have our initial design value. So our Q in flow rate will be 39.6 kilojoules per second. Our Q out in actual cycle, we have negative 63.228 kilojoules per second. Our Q out isentropically, we have negative 57.2 kilojoules per second. Our compressors for the actual, we got positive 23.628 kilojoules per second. And for isentropic compressor work, we have 17.6 kilojoules per second. And our mass flow rate in kilojoules per second, we got 0.04 kilojoules per second. And our coefficient of performance, COP, we got a value of 1.68. So this is a video of refrigeration cycle using ammonia. This incident happened using ammonia, which is actually, ammonia is a hazardous and deadly working fluid. However, companies such as where you have big refrigeration like Tyson, they use ammonia working fluid to store their, food, their chickens. So this incident here, the compressor, their working fluid ammonia had leaked, and that became very dangerous for the workers. And I believe 2 workers got injured. As you can see here, they didn't even wear their equipment, their PPE, which is also one thing we have to learn. You have to wear your PPE. So that had happened. I'm trying to see exactly where. So you can see here it's leaking. So yes, that's a video of how ammonia is a deadly hazard, but it's how we prepare to use it safely. So we decided to use ammonia because it has a very low global warming potential, GWP of 1, in a calculation of every 100 years. And our efficiency, we decided to use 0.75, which is best for our compressor to work well and to produce a much pressure and temperature. And then we decided to use a delta T approach of 15. So that means we'll have to use a negative 30 degrees Celsius on the evaporator and 45 degrees Celsius on the compressor. And the reason why we chose delta T of 15 is because we don't want our evaporator to act as a vacuum. So that led us to use a pressure of 0.13, which is slightly above the ambient pressure system. So we didn't want our evaporator to work as a vacuum.
And also, just wanted to add it, we didn't also want to put too much energy into the system because it would cost us more, or it would cost us, the designer, more. So that's why
economic plays a big thing.
Mm-hmm.
So here are references of our research data. And thank you.
Thank you for taking the time to listen to us.
Yes. Have a great day.